Today we work on our second day of section 2.4, where we're looking at complex numbers and operations. As you remember yesterday, we talked about what complex numbers were, and we worked with multiplication, addition, and subtraction. Today we're going to look at what happens when we are dividing by a complex number. So in order to understand the process we're going to use, we have to learn the definition of this thing called complex conjugates. And complex conjugates are complex numbers with the same real part and opposite imaginary parts. So get that in your notes. Complex numbers, and remember, complex numbers are a plus bi with the same real part and as a reminder, the a is the real part and opposite imaginary parts. Okay, so remember the bi, that's the imaginary part. So for example, a complex conjugate pair is a plus bi and a minus bi. So you switch the sign in the middle, the sign attached to the imaginary part. But here's the key. Let's look at what happens when we do a plus bi times a minus bi. So when we multiply two complex conjugates together, a times a is a squared. We would get minus abi plus abi. And we saw this a little bit yesterday. And then a positive times a negative is minus, b times b is b squared, I squared. And what happened is when we had these exact same things but with opposite signs in the middle, these middle terms cancel out. So we're left with a squared minus b squared, and remember I squared is a negative 1. Negative times a negative is a positive. So we're left with a squared plus b squared, which is going to be a real number. So the product gives us a real number. It gets rid of the i's. And that's going to be our goal. Okay, so a squared plus b squared will just give us a number. So let's look at examples again of complex conjugates. If I have 7 minus 8i, its complex conjugate would be 7 plus 8i. Okay, so hopefully you're able to think of that in your head. Negative 2 plus I. Think for a second about what its complex conjugate is. Hopefully you knew negative 2 minus I. Again, make sure you know that it is only the sign in the middle that changes. Common mistake is people change both signs, okay? Just on the imaginary part. All right, so those are what complex conjugates are. Now let's look at how we use them. Simplify a quotient with a complex number. How can you write the quotient 10 over 2 minus I in the form a plus bi? So we're starting with this ugly fraction where there's a complex number on the bottom, but we want to just write it as a regular good old-fashioned complex number, a plus bi. This note you want to get in your notes. In order to do that, we are going to multiply the denominator by its complex conjugate, and that will result in a denominator that is a real number. Now we have to remember that when we multiply a fraction by something, you can multiply it by anything you want equal to 1. So whatever you multiply the bottom by, you have to multiply the top by as well. So what you multiply the bottom fraction by, you must multiply the top by. Okay, so let's look at this. So we have 10 over 2 minus I. Again, I want to get it in a plus bi. The only way to do that is to get the bottom of the fraction to be a real number. So that is why I can multiply 2 minus I by its conjugate, which is 2 plus I. Hopefully you knew that. Okay? But the only reason I would be allowed to multiply this fraction by 2 plus I on the bottom is if I also multiply the top by 2 plus I. Because really I've multiplied by 1, because 2 plus I divided by 2 plus I is 1. Okay, now we have to do the algebra of this. I like to put parentheses around anything that's a binomial. Because there's just a 10 on top of the first fraction, I need to distribute. So 10 times 2 is 20. 10 plus times I is plus 10I. So that's my top. It's nice when there's just a single number on top. But now remember, on the bottom, I could multiply it out. 2 times 2 is 4, plus 2I minus I squared. Remember, these cancel. 4 minus I squared is negative 1, which is the same as 4 plus 1, which is 5. So that's the bottom. Now remember, we also learned that complex conjugates are a squared plus b squared. Well, my a was 2. And my b, if there's no number attached to the I, it's a 1. So it'd be plus 1 squared, which gives me 4 plus 1 is 5. So that would be a shortcut to get to that same answer, if you remember that it's a squared plus b squared. All right, so we're in a good spot, but we are not in the form a plus bi yet. So now we have to understand how to take a big ugly fraction like this and break it apart into 2 parts. In order to do that, we can break it apart, but we must keep that 5 with both pieces. Okay, so I can do 20 over 5 plus, but then when I go to the other side, I must also keep that 5 under the 10i. So plus 10i over 5. A common mistake is people only divide one piece by it. Now I can simplify each fraction. 20 divided by 5 is 4. 10 divided by 5 is 2. So my final answer is 4 plus 2i. So you can see by using that strategy where we multiply the numerator and denominator by the complex conjugate, we are able to get it into a plus bi form. So that's the process we're going to use. Now let's practice another time together. All right, here is another one. 4 minus 3i over negative 1 plus 2i. Again, the strategy is if you can turn the bottom into a real number, it will allow you to get it in the form a plus bi with some simplifying. So we are always going to take it and multiply by the complex conjugate of the denominator. So even though on top I have this complex number with a real and imaginary part, it doesn't matter. It's only the bottom. So I need to think about negative 1 plus 2i and ask myself, what is its complex conjugate? Hopefully you remember, you only change the sign in the middle. So it's still a negative 1, but it's minus 2i. If I multiply the bottom by that, I must also multiply the top by that. And now because the 4 minus 3 is a binomial, I also put that in parentheses. Now again, the shortcut for the bottom, remember it's a squared plus b squared. My a is the negative 1. My b is a 2. So I get 1 plus 4. Once again, I get 5. Able to simplify this without foiling it or expanding it completely, or you could do that if you want. Now when I look at the top, I do have a binomial times a binomial, so I am going to have to do all my distribution there. So 4 times negative 1 is negative 4. 4 times negative 2i is minus 8i. Negative 3i times negative 1 is positive 3i. Negative 3i times negative 2i is positive 6i squared. Okay, so I multiply all that out. Now I combine like terms on top. So really we're actually using what we learned yesterday.
It is now time to begin the proof.
So we had the negative 4, and we're doing what we did yesterday. Negative 8i plus 3i is negative 5i. And don't forget, 6i squared is the same as 6 times negative 1. Still all over 5. Negative 4 minus 5i minus 6 over 5. I'm going to come down here. Gives me negative 10 minus 5i over 5. Okay, so you could have condensed that into some separate steps, I'm sure, but that is where we're at. Now again, this next step is a common mistake. I go to break it apart. I need to keep the denominator of 5 with both pieces as I break it apart. So I take the negative 10 over 5, and then because it's a minus, I can either do plus a negative 5i over 5, or you could have just done minus. And this now gives me negative 2 minus 1i, or just minus I. You could put a 1 there if you want. All right, I want you to try one more on your own. So take this one, 80 over 2 minus 6i. Pause the video, try it on your own. remember to multiply by the complex conjugate and simplify to a plus bi. Hopefully you first recognized that your complex conjugate was 2 plus 6i on the bottom there. So the bottom, a squared plus b squared is 2 squared plus negative 6 squared. 4 plus 36 is 40. So that's how I got the bottom. And then on top, I just had a single number 80. So I distributed to the 2 and the 6i. I got 160 plus 480i. Once again, I went through that piece where I broke it apart. I did the 160 divided by 40. And then I also did 480i divided by 40. When I simplified those fractions individually, I got 4 plus 12i. Just so you know, you don't always end up with nice, neat numbers. When you go to do Pearson, you will sometimes end up with fractions. For example, for one of my answers, I got 6/5 plus 2/5 I. For another one of my answers, I got 8 over 145 minus 9 over 145i. So really all you want to make sure you do is once you break it apart like this, see if you can simplify the fractions individually. Sometimes they divide out like nice whole numbers. Sometimes you're just going to reduce the fractions, and sometimes they won't reduce at all, and you just leave it as 2 individual fractions. All right, so that's kind of section 4. Again, we're talking about complex numbers, a plus bi, and we learned how to add, subtract, multiply, and what we do if we're given a division problem that has a complex number on the bottom. You can see down here what I was just talking about, how sometimes it works out kind of ugly. So you can see their example ends at 7 over 26 plus 17 over 26i. That is how you would want to write an answer if you get a fraction like that. All right, go ahead and start working on your Pearson 2.4 Day 2 assignment. Thanks.